So last time we mentioned this finding large independent sets in a triangle free graph, the result of I-type cohomology similarity. So let's recall this theorem. I-type cohomology similarity. They prove that for every n-vertex triangle free graph G with average degree T, then you can find an independent set of size, let's say 1/100 n log T over T. Okay, so the greedy algorithm will give us, or Turan will give us n over T, then the log T extra factor thanks to triangle freeness. And this log T is also optimal. One can use this, a corollary of this, I will leave as exercise, if I didn't mention it last time, is that this implies that the Ramsey number for triangle versus KT is at most some constant times T squared over log T. Okay. Right. So one of the key lemma, the nibble step, is this lemma. In building such a large independent sets, it says that for every n-vertex triangle free graph G with average degree T, which is less than, let's say, n over 100, then we can find, for every such graph, we can find a subgraph K. So here's the picture. We can find a subgraph K. This is, let's say, the common neighborhood of, this is the neighborhood of vertices in K. Those are the vertices that has at least one neighbor in K, right? And the remaining graph is M. Notice that there's no edge between K and M because of this guy. So we can find such a subgraph K such that it is small. So the number of vertices is n over 100 T, but the number of, it's very sparse basically. Size is roughly n over T, and the number of edges is also linear in its order, and most 1 over 50 times number of vertices. So these two together implies, as we said, that in K alone, we can find an independent set of size, let's say half of its vertices. So this is the nibble step. In every time, we can find independent set linear in n over T, and repeat this inside M. We're going to do log T times. Last time we've seen how we get the final result from the nibble step. So here's the statement property for K, and M equals to G with K removed, and also with its neighborhood removed, satisfies it has at least n over 2 vertices, the remaining graph. And let me write m prime and t prime for the number of vertices in M and the average degree in M. This ratio, which is the ratio where we're going to find independent set, is not dropping too much. It's at least some 1 minus t minus some constant t over absolute constant times n over t. This is the nibble step. Okay. So let's see a sketch of the proof for this. There are lots of calculation. I will skip some of them. So the idea for this nibble step is simple. We simply take a random set of size n over 100t. We're going to prove that with positive probability, all this property holds. And that's it. And how we can control and prove this positive probability that everything holds, we basically need to control the second moment. We want to say that all these random variables, so if you choose k, random k, its order is a random variable, number of edges is a random variable, m depends on k, so it's also a random variable, how many vertices left, what's the ratio of this remaining graph, everything is a random variable. And we want to say that for each one of these random variable, its variance is not so large. And by Chebyshev, we know that when the variance is small, then this random variable is concentrated around its mean. And if it's concentrated around its mean, everything here will hold. That's the idea. Okay, so let's see the proof. Any question? As I said, we're going to take, so first, let's make an extra additional assumption, which we're going to remove at the end of the proof. So let's assume for now, additionally, assume additionally, let's put a maximum degree condition on our graph G. Let's assume that our graph has maximum degree and is almost regular, 10 times the average degree, T. So let's set this 10T number as let's set capital T to be 10 times the average degree. So let's assume for now, we have an almost regular graph. As I said, we're going to choose the vertices in K randomly. So pick, choose a set of a random set, sorry. Choose a random set of n over 100t. Let's call this guy K, little k. Little k. So choose a set of little k vertices and let the induced graph, the graph induced, to be capital K. Okay. Now, what are the three random variables that we cared about? We cared about the order, no, sorry, order is fixed. We choose, so this is little k, we choose a random little k vertices. This is always the case. We need to control the number of edges in these random sets that we pick. We also need to control the vertices in the remaining graph and the average degree in the remaining graph. So we have a control on this ratio. Okay, so the three random variables that we cared about are, so we, how do I write it? So let's first write the claim, an easy claim. With positive probability, actually with probability with positive probability, we will see that it's at least 1/4 probability. We have, there exists a choice of K, this random subgraph, such that we have simultaneously, such that the random variable, first of all, number of vertices in the remaining graph M, here, this is M, and is around its mean. So the bad event, the good event is close to its expectation, deviate by 2 standard deviation of it. And we want its edges to be also close to its expectation. Okay. So this is the most expectation of EM minus 2 times standard deviation. We also want to control the number of edges in this random graph K. This is, again, concentrated around its expectation by 2 standard deviation. The proof of this is easy. Remember, by Chebyshev, for any random variable, the probability that it's around its mean, deviate away from its mean by 2 standard deviation is at least, the probability is at least 3/4, right? With probability at least 75%, a random variable is within 2 times standard deviation of its mean. Okay, then we are done. You have 3/4 probability that this holds, 3/4 that this holds, 3/4 is holds. Well, okay, in other words, 1/4 this fails, 1/4 this fails, 1/4 this fails. Union bound, at least 1/4, none of this fails. Okay, so that means we just need to calculate, the expectation of this, the variance of this for each one of these 3 random variables. So let's give names. Let's call this random variable X, the number of vertices in M. It's called random variable Y, the number of edges in M. And let's call this random variable Z, the number of edges in K. All right, let's do some calculation. Good. Expectation is easy. Let's start with the first moment. Let's first look at X. Let's work on the first moment. Now, recall X is the number of vertices in M. And let's recall this picture. X is basically sum of a bunch of indicator functions, each one of which is responsible for a vertex being in this random set M. Let's write it down. We have X is the sum of xi. I is a vertex, where xi is indicator function. Indicator function, whether the vertex I lies in M or not. Okay. Or to be precise, lies in the vertex set of M. Good. Now for this one, what's the, so the X, we want to compute first moment, expectation of the order, expectation by linearity of expectation. We just need to compute each one of these indicator random variable and sum them up. Now, what is the expectation of xi? Indicator variable, random variable means this is the probability that I lies in this random set. Okay, when does a vertex I lies in M? Well, a vertex I lies in M. Let's look at this. This is the neighborhood, okay? Now let's give a name. Let's write M bracket I for the closed neighborhood. That means the neighborhood of I union I itself. Okay, closed neighborhood includes the vertex itself. I notice that, let me write the conclusion first. This event occurs if and only if the closed neighborhood of I is disjoint from our random set K. Okay, so here's K, our graph K. Right? I is here. That means, well, first of all, I is not in K. So I is not in K. Second of all, the neighborhood of I cannot be here. This means a neighborhood of I is in K. So the neighborhood of I is either here or here, disjoint from K. Is that clear? What is then the probability that the closed neighborhood of I disjoint from V of K? This is easy because K is uniformly chosen, little k sets. So this probability equals to, let me also write n sub I. Let's write n, oops. Let's write n sub I to be the size of the closed neighborhood. This is just the degree of I plus 1, right? So, notation. This is basically saying this occurs when K is chosen outside of this. And the number of such choice is m minus ni. We have to choose little k vertices. That's the total number of choice. Divided by, this is uniform distribution over all possible choices, and choose k. So far, so good. Not so hard, right? Now, so this equals to, we have, as a conclusion, expectation of x equals to sum over all I vertices, this probability, m minus ni, choose little k, divided by n, choose k. Okay? Now let's give an estimate on this expectation. Well, this is at least by convexity. We sum over, this is the degree, basically degree plus 1. And this is a convex function. by Jensen's inequality, for example, this is lower bounded when the graph is regular, but when every ni is the average. So convexity this is at least n times m minus t minus 1 average value divided by n choose k. Okay. Now this is binomial coefficient. One can compute that this is larger than n times 1 minus k over n minus t. This is easy calculation, t plus 1. Let's further lower bound the right-hand side. Since we choose t, recall that t is average degree is smaller than n over 100, right? So that means, and k is n over 100t, okay? So we have this is bigger than n times 1 minus this guy. T is smaller than half of n, so let's replace this by n over 2. K over n over 2, t plus 1. Now use this inequality. 1 minus a small number to some power is roughly e to the negative epsilon t. Okay? Write it on the side. 1 minus a small number to a large number is roughly e to the negative t. So we have this is bigger than n times e to the negative k over n over 2 times t roughly. Let me be not so precise. You can fit in the right constant, so it's correct. Now kt over n. What is kt over n? Kt over n is a small number, 1 over 100. So this whole thing is bigger than, let's say, 0.9 n. Good. We finish estimating the number of vertices remaining M. At least 90% of vertices remaining M. That's the first part. Good. Now let's look at its variance, shall we? Let's copy this one here. With the expectation at hand, the variance is easy to compute. Variance of x equals to, so x is sum of xi. The variance is basically the how do I write it? The this is the expectation of x squared minus expectation of x squared, right? We know what this guy is. Just square this. What's the first one? Well, first one is the expectation of sum over all ij, xi, xj. So this guy we know. Let's look at what's this guy. Expectation of bilinearity of expectation. Let's look at one term. This is basically the probability that both I and j lies in the vertex set of M. So this is the probability that I is in, both ij are in M. Okay. This occurs when what? As I said, similar than as before. For vertex to be in VM, that means its close neighborhood is disjoint from K. So this is the probability that the close neighborhood of I union the close neighborhood of J, they are both disjoint from K. Okay, no problem. And this probability, let's write Nij to be the size of this union equals to, as again, using the fact that the vertex set of K is uniformly chosen. For a uniform chosen choice that this holds, we need to choose a complement of this set, a random K set, which is M minus Nij. We choose a K set divided by the total number of K sets and choose K. Okay, so altogether, plugging this, we have variance of X equals to sum over all Ij. Inside, we have this probability minus expectation of X squared. So it's this X squared means Ij, this times the same thing, but Nj here. So we have what? M minus Ni, okay. And M minus Ni, choose K over N choose K times M minus Nj, K, N choose K. Bracket. Okay. This, one can also do some calculation. Not The calculation is not very complicated, but it's not very illuminating. It doesn't tell us. There's no just technical calculation. So let me skip it. So this is after some calculation. Boring calculation. This is less than n times the average degree t. Okay, let me not do that. Now let's move on to the second random variable, y, which is the number of edges induced by the remaining graph. All right. Random variable y. So how do we write random variable y? This is not very hard. Okay. So let's recall y is the random variable counting the number of edges in M. We can again write y as sum of random variables ij, but we only sum over pairs ij that form an edge. The indicator function, it's actually just this, right? Xi, Xj. Summing over all edges, it's ij is endpoint. You need both endpoints. This is, recall, indicator function for vertex to be in M. So you need both of them to be M, then it's counted. That's it. So we can then compute. We know exactly what's this expectation. We've just did it before. The expectation of this is this guy. So we have expectation of y equals to sum over not only pairs ij that form an edge, m minus nij, choose little k, divided by n, choose k. Very good. And we can again, by convexity, Same thing. This is a convex function. It's minimized when every nij is around its expectation. Well, actually, this nij is the union of ij's close neighborhood. Each one of them is at most t minus 1, capital T plus 1. But since we're summing over an edge, okay, so this is t minus 1 here, t minus 1 here. This is actually 2t. So it's easy to, there's no even complex convexity here, all right? I don't even use convexity. So let me draw this. We sum over ij, its neighborhood, and maybe there's overlap, I don't know. Oh, but this triangle free. This is not overlapping, right? All right. This is of size. So we have nij at most 2t. Okay, maximum degree. Yep, I think it's correct. So this is at least we have how many atoms? The number of summons is number of edges, which is n times t over 2 times m minus 2t, choose little k, over and choose k. And this we can do the, this is bigger than nt over 2. Similar calculation, 1 minus little t over m minus 2t, binomial coefficient 2t, which is bigger, similar calculation, nt over 10. All right, this we can compute. Okay. Now, let me skip the variance of y. It's similar, just a little bit more tedious. So I will leave it for you. Variance of y, fill in the details. We have one last random variable, z, which is, where is it? Number of edges in this random set of k vertices that we pick. Okay. So let's recall z is the number of edges in this random set, random graph K. This expectation of z is not hard to compute. I will not do the variance again. So the variance of z for you to fit in. Expectation is what? Expectation is, again, sum over all edges. Sum over all edges. And for an edge to be in K, basically so this is K, right? You want both ij to be in there. So we need to choose this K set with ij picked. This happens with probability. What? In the remaining vertices, n minus 2, we choose k minus 2, right? Together with ij, forming this k set, divided by total number of choices. And for each ij, this is the same probability. So you just multiply by the number of edges equals to, okay, this is good enough. Variance I will skip. Then doing some calculation, we arrive to the following claim. We've computed the first moment of x, y, z. We compute the variance. We can then obtain that for x, y, z, its standard deviation of x is at most some constant, let's say 1000 times square root t over n times its expectation of x. And same holds for y and z as well. So we do have all this random variable that we want is concentrated around its mean because the variance is small. Finally, let's derive the conclusion. So let me convince you why things is expectation of z. Right, so what is x, y, z? I forgot. Yeah, okay. X, y, z is Vm, Em, Ek. So let's write down the calculation so far. We have the expectation of Vm, which is x, is around what was the V? What did I write? I get the lower bound on the expectation, right? Right, 0.9n. So at least expectation is 0.9n vertices left. Y is the number of edges in M, which is at least, what was it? Expectation of Y, here. At least some linear in number of edges, nt over 10. Also lower bound, yes. Nt over 10. Okay. Now, good. Using this, an expectation of z, this is roughly what? Let's look here. Nt over 2. This is roughly k squared over n squared. Okay, the ratio of this binomial coefficient. So this is roughly k squared t over 2n. Kt over n is 1 over 100. So it's roughly k is n over 100t, right? So what is it? N over 100t? Well, some n over t and some large constants, okay? Let's say 1000, whatever. Change this 1000 to some correct constants. So roughly this much is some constant times n over t. What is z? Z is the number of edges in K. Okay, you have these three. Now we are done because what do we want to say? We want to say that K induce a very sparse graph. Remember, K is a set of n over 100t vertices. So this is constant average degree. K is sparse. We can find a large independent sets. And we want to say that the remaining graph, M, has at least half of the vertices, which is true, 0.9n. And we want to say the ratio of whatever n over t, n prime over t prime. This can be derived also from the estimate on the expectation of v of m and e of m. I will skip that part. So lastly, I want to say why we can assume, remember at the beginning, we assume the graph is almost regular. So now let's remove. This is at most 10t condition. Removing this condition is easy. If the graph has large degree vertices, we simply delete them, and there cannot be too many of them. So if not, so you start with G, then you keep deleting vertices of degree strictly bigger than 10t. You get G prime. How many vertices that we delete? Let's say number of vertices deleted is, did I use M? Let's say M. We have M times 10t edges deleted, right? This must be less than E of G. Okay, you cannot delete more than the number of edges you begin with. This is nt over 2. So implies that number of vertices that we delete is at most, if you have a degree more than 10t, deleted. Now, if you still have 10t, wait a second. Yes. So M is at most, move 10 to the other side, delete t, n over 20, right? So we delete less than n over 20 vertices. Wait. Do I want to say number of edges? So if you have a degree 10t deleted, now in the remaining graph, more than 10t deleted, remaining graph more than 10t deleted. Yes, so the number of edges deleted is at least this. Good. Then we have the number of vertices in G prime is at least m minus n over 20, which is at least 0.9n. Now by doing this, we can check that. So this, I will leave it as exercise for you to check that this ratio of n over t is not dropping. So n prime over t prime is at least n over t when you do this deletion. Good. You just simply start with G prime at the beginning of the proof instead of G. That's it. Any question? Okay, if there's no question, we're going to move on from this second moment part to the next part of probabilistic method. This is a dependent random choice. So dependent random choice is a simple lemma, but surprisingly, it turns out to be very powerful. So what is dependent random choice? Um, let's start with new chapter. Dependent random choice. Okay. Let's first recall covariance Short-Run. So one can think of dependent random choice as a strengthening of covariance Short-Run's averaging argument. Covariance Short-Run proved that the extremal number of KST, if S is most T, L is 2, is big O of n to the 2 minus 1 over S. And how they do it is by averaging. They find so their arguments averaging arguments finds one S set which has lots of common neighbor, at least T common neighbors, right? So they find one. In many applications, it'll be nice. Actually, in the proof, we can guarantee many S sets to have large common neighbor. And in many applications, we would like these S sets that are rich in common neighbor to be clustered together. That's what dependent random choice is doing. Dependent random choice is giving us, under some density condition, a large set of vertices in which every set of size, bounded size, has a large common neighbor. Okay. So under some density condition, so dependent random choice yields a large set of vertices, which is the set U below in the lemma that I'm going to state, in which every small set has many common neighbors. Here's the lemma. This is the most basic form of dependent random choice lemma. Let's take natural number n, d, m, n, r, and a, natural number, lots of parameters. Now let's take an arbitrary graph G. So G is an n vertex graph with average degree d. Now the hypothesis is that for any n vertex graph with average degree d, hypothesis is that if there exists a natural number t satisfying this inequality, d over n to the t minus 1, t minus n choose r, m over n to the power t is at least a. So here, this is the key inequality. Then we can find this nice set U of vertices such that it's large. U is at least of size A. And every R set in U has at least M common neighbors. Every R set in U has at least M common neighbors. So here's a picture. We can find this nice set U such that every small set, some R sets inside, if you look at the common neighbor, it's large. This is, let's say, R set R. This is the common neighbor of R, is at least M vertices. So here, let me use a non-standard notation. Usually we write N of R to be the vertices that has at least one neighbor in R, the external neighborhood. Let's put a star for the common neighborhood. This is the intersection of NV, V in R. Okay. Good. This is for any R inside. Any question about the statement? Let's first prove this idea. The idea is we're going to choose U randomly. And we're going to prove that with positive probability, one of these random U will have all this property. So how are we going to choose this random U? This is where this dependent random choice, this name dependent comes from. We're going to not choose U totally randomly. It depends on some other sets. So we're going to choose a set T of T vertices with repetition, some random set T. So we're going to let, here's a picture. We have, here's a picture. We're going to choose a random set T. Let U to be the common neighbor common neighborhood of a random set T of T vertices chosen with repetition. This is for the ease of computation. So we choose a random set, and our U will be its common neighborhood. So this is U. Okay. Why is this random? Well, intuitively, why is this good? Let me explain that. If U has a small, if we have a, let's consider a small, consider an R set inside. If R is bad, that means its common neighborhood is small. Then it's unlike, first of all, what's the property of R? We know that its common neighborhood must contain T, right? We know the common neighborhood of R must contain T. Because if you zoom into a subset, the common neighborhood is only getting larger. T is adjacent to everything in U, in particular adjacent to R. Okay? So this is a subset of these. If the common neighbors of R is small, then it's unlikely that this random set T will lie in these small sets. So unlikely there's a bad set. In other words, the number of these bad small sets is very small. Then we can use alteration first moment to delete them to obtain the final set U that we want. So we have to modify them a little bit. This implies unlikely unlikely this occurs. Thus, there are only few in expectation bad such subsets are. Use first moment alteration. This is idea. All right. Now let's look at the details. Proof. Let T, as I said, be a random, be a set of random set of T vertices with repetition allowed. What this means is that you first choose a random vertex with probability 1 over n among all vertices, uniformly random. Let it be the first vertex of T. For the second vertex of T, again, among all vertices, you choose the same probability 1 over n. So maybe T is a multi-set. So we have T vertices. Now we define two random variables. We let X to be, okay. Let's first define the set U. Let's call it U0 because we're going to modify it. Is the common neighborhood of this random set T. Okay, so we have T. Look at its common neighborhood. Common neighborhood. This is my set. Actually, I want to make it larger. So U0, common neighborhood. Good. Let's define random variable which counts the size of this random common neighborhood U0. And let Y counts the number of bad sets, which is the number of R sets R contain in 0 with small number of common neighbors such that their common neighbor is less than the threshold M that we want to achieve. These are the bad number of bad R sets, right? It suffices to show expectation of X minus Y is at least A. Why? If this is true, that will means this will imply that there exists a choice of T, this random set, such that X minus Y is at least A. Then what we do is, remember, X is the size of U0. For every bad R set, we remove a vertex from U0. In this way, we'll kill all the bad R sets. Then all the remaining R sets in the U0 minus one bad vertex we have large common neighborhood. So remove one vertex from each bad R sets. We will get our final set U, which is of size at least A. And that's the set that's desired. Okay. So let's estimate the expectation of each one of them. Expectation of X, this is simple. We sum over all vertices in G. A vertex lies in U0 if and only if X is adjacent to all vertices in T, right? That means T is in the neighborhood of V, okay? This vertex is adjacent to everything, then it lies here. That means T is in the neighborhood of V. This occurs with probability sum over V. Well, for each vertex in T, it lies in here with probability dV over N because the vertex in T is uniformly chosen. And since we choose them with repetition, independent of one another, we raise to power T. There are T vertices chosen. So this equals to d of V over N to the T equals to M to the negative 1 over N to the T sum of V dV to the power T. This is a convex function. Now by convexity, Jensen's inequality, it's at least 1 over N to the T minus 1, the average degree, which is D to the T. Good. What about Y? For Y, which counts the number of bad sets, let's fix an R set. Let's say R. Okay. If this R set is bad, that means its common neighborhood is smaller than M. Then the probability that this bad R set lies in our random set U0. So this is U0. This is this bad R. And remember, U0 is the common neighborhood of this random set T. This will require what? T must lie in the common neighborhood of R, right? So this is the same as the probability that T is in the common neighborhood of R. And this occurs with probability equals to size of the common neighborhood of R divided by N to the T, right? Which is less than, we know that this is bad, size less than Mn to the T. Okay, now we have expectation of X minus expectation of Y. Linearity of expectation is at least d to the T over N to the T minus 1 minus, let's use union bound. For each bad y, I forgot to do the union bound step. Let's do it here. Union bound implies the expectation of y is at most. What's the number of R sets that this is true? It's bad. Well, just use total number of R sets to upper bound it times this probability of a single one being bad. So we have these. Then by hypothesis, we know this is bigger than A. We are done. Any question? Okay. Here's the, let's see the lemma again. Dependent random choice lemma. Now, some exercise homework for you to prove. First exercise is to use dependent random choice to get the upper bound on the extremal number of bipartite graphs. For any bipartite graph H with degree and most R from one side of the bipartition, prove that extremal number of such bipartite graph is big O of n to the 2 minus 1 over R. Okay. This is a result of Freddy, and later along Krivolovich and Sudokov used dependent random choice to give a shorter proof. Second exercise. Well, recall second exercise is by Ramsey. I want to find, so here's the exercise. For any graph G, n vertices, and number of edges is at least epsilon n square. Okay. Prove that there is a complete bipartite graph x, y. Y is at least some constant times log n over log 1 over epsilon, I believe, something like this. Log n order complete bipartite graph. This is easy. This is just covariance. That's a corollary of that. But I want you to prove that we can furthermore guarantee that x and y, they are either independent sets or they are a clique. So they are homogeneous. And x and they either complete, either clique or independent sets. I'm not requiring them to be both clique. I'm just saying either clique or independent set for x and either clique or independent set for y. Well, a naive way of doing this is first you use covariance, you get log n here, log n here. Now you use Ramsey, you don't know how x and y look like. You use Ramsey, you will get log n. So you can get log n with this property. But this two round of applying average Ramsey averaging is not good. You get log n. Use dependent random choice to prove that you can skip one round to get directly log n. All right. So here are the two quick applications. You can try to work it out yourself. Now let me illustrate application of dependent random choice. There's a nice survey by Jacob Fox and Benny Sudakov. There, it contains lots of applications of dependent random choice. Now, let me mention some applications that's not in that survey. It's application in Ramsey-Turan theory. Let's first recall. The definition of Ramsey-Turan number. So the definition of Ramsey-Turan number M. This is the maximal number of edges of a graph G, where G has m vertices, G is H free. Okay, so far this is just the external number of H, but we also further require that alpha of G is m most m. Okay, why this? So this is initiated by Schorsch. The motivation is in Turan theorem, the maximizer is Turan's graph, which has huge independent sets, linear in n size. So she was asking, what if we replace it by little n? This is the most classical case. If we require that we don't see linear size independent sets, how much it's going to affect the maximum number of edges? And later, here, the application I'm going to mention is we're going to go below this classical regime that the alpha n is sublinear, go to much smaller, polynomially smaller than n. In particular, the inverse function of triangle Ramsey number, square root n log n. So let's mention this. So Erdős and Schorsch ask this question of whether the Ramsey-Turan number of K5 square root n is little o n squared. Okay, in other words, is it true that for every n vertex graph G, if it's K5 free and independence number is smaller than square root n, then you cannot have positive edge density? That's their question. This was confirmed in a stronger sense by, so this is true now, theorem by Barlog, Wuping, and Shimonovich. About 10 years ago, they confirmed this is in a stronger sense. So what they prove is the Ramsey number of n K5 little o of square root n log n is little o n squared. Okay. This is optimal, which we call a phase transition here. What do I mean? Remark. We know that if you change little o to constant 1 times square root n log n, this is actually n squared over 4, 1 plus little o 1, plus little o n squared. So as the independence number drop from square root n log n to little o of that, the edge density suddenly dropped from 1/2 to 0. The graph cannot be dense anymore. Okay, of course, this is a stronger version of that because it's already sparse at a much larger independence number requirement. Okay, why is this true? The construction is easy. Just take n over 2 vertices on each side, add all edges. Now inside here, you put the triangle Ramsey graph. What does it mean? This is an n vertex graph or n over 2 vertex graph, which is triangle free. And independence number is of order of magnitude square root n log n. Okay. So you don't have independence number is satisfied at most square root n log n. And there's no triangle. No triangle means no K5, right? If you have a K5 by pigeonhole, you must have a triangle on one side. So there is this transition of density when you drop at this tiny window. We call this phase transition. Okay, let's try to prove this. Any question? So what we will prove is, let me state this more rigorously, not using little o. I'm going to prove that so let me state their theorem again, BHS. For any n vertex graph G, if you are K5 free and your independence number is at most, let's say, epsilon to the 4 square root n log n, then this is little o, right? Little o of square root n log n. Then the number of edges is also little o. E of G is at most epsilon n squared. This is what we want to prove. Okay. So we're basically going to apply dependent random choice. We want to apply dependent random choice with this choice of parameter. Little a to be epsilon to the, let's say epsilon to the 8, and R is 3. So you want all the triples inside has large neighborhood. The average degree of our graph G we know is so we actually want to prove the contrapositive. So contrapositive means if the number of edges is at least this, then there's a K5. Yeah, okay. Wait. Let me adjust this. suppose suppose otherwise, EOG has more than epsilon n square edges. Okay, we're gonna apply dependent random choice with A these, R these, D is what? D is 2 epsilon n, right? We have more than epsilon n square edges. We're gonna let M to be square root n log n. We're gonna let A, do I have everything? I know M, D, R. Oh, I wrote the extra n here, so delete it. Good. Now I'm gonna show that with little t equal to 7, this works. And t equal to 7. This implies what? D to the t minus n to the t minus 1 minus n choose R is 3. This is bigger than 2 epsilon to the power 7 times n minus n cubed. M over n is log n over, what is this? Let me see. Yes, this is log n over n to the power 7 over 2. Okay, this can be checked, which is bigger than, this is n to the 3.5, larger than n to the 3. Log n lower order term. So that basically goes to 0. That's the leading term. Bigger than epsilon 7 n, which is bigger than a. Good. Okay. So what do we have? We know by dependent random choice, we can find a set U of size at least A. So there exists a set U of size A. Let's draw it. U at least A. What's A? Linear in N, all right? Such that every triple of it, for every triple, its common neighborhood is at least M. Okay. So we're gonna derive a contradiction. How do I derive the contradiction? Well, first of all, apply by Ramsey such that every triple in U has at least M common neighbors. Okay. First, by Ramsey, that means R3 K equals to K squared over log K. Okay. We know that either U has a triangle or there's a triangle in U, or there is an independent set of size at least square root n log n. This order of magnitude, which is a contradiction because we know our graph independence number is a little o of square root n log n. Okay, so that means we must have a triangle here. But for this triangle, let's apply this property. It has a large common neighborhood. Let's call this T. Now inside n of t, common neighborhood, this is at least m, right? M is square root n log n. Again, larger than alpha of g. What does that mean? Because our alpha g is little o of square root n log n. That means there must exist an edge inside. And this edge E together with T will form a K5 contradiction. E plus T, you get K5. Let me be lazy and write it like this. That's it. Any question? So once again, let's prove it. Basically, by dependent random choice, you can find a set of size linear in N in which every triple has large neighborhood. Now, since this set is linear in N, by Ramsey, either independent set is bigger than square root n log n, which is not the case. So that means we must have a triangle. And this triangle has common neighbor larger than square root n log n, the independence number. You can find an edge. Together, you get a K5. Question? Okay, if there's no question, we're gonna continue next Tuesday. What date is next Tuesday? Oh, wait. What? Next Tuesday is calendar. Last day of the year. Yeah. I'll see you on December 31st. Next class. Thanks for listening.